Electromagnetic Induction by Santiago Sinisterra.
Magnetic fields. Magnetic fields are the base of electromagnetic induction. They were discovered by Michael Faraday in 1831 by wrapping two wires around the opposing sides of an iron ring, passing current through one side and observing how the other received current. He then induced that the alternating current generated a magnetic field, which likewise generated the current in the other iron wire. And this way he discovered the magnetic field's existence. Magnetic fields are represented by lines. The arrows in the field lines always point in the direction that a force would act while interacting with a magnetic north pole. The distance between the lines tells us relative strength of the field. The closer, the stronger. The further apart, the weaker. This will be the magnetic field strength, the force that it exerts on a current placed at a right angle from the magnetic field, shown by the symbol B, as mentioned before by my companions. Magnetic lines have flux. Flux is the total number of field lines in the magnetic field. It is measured in Webers. In more technical manners, magnetic flux is the magnetic field strength normal to a surface multiplied by the area of that surface. How many lines pass through an area is denominated as flux density, measured in Webers per meter squared. This way we may mention that magnetic field strength is equivalent to magnetic flux density. Thus, if the magnetic field has to be normal to the surface, magnetic flux formula will be magnetic flux, represented by the phi symbol, is equivalent to the magnetic field strength times area times cos of the angle between the flux and the normal. When we are using magnetism to generate electricity, the area of the flux density is the area inside the loop of the wire. The greater number of loops, the more area there is. This lets us with n number of turns into the formula, leading to the flux linkage formula to be flux linkage is equal to phi n, or in extended manners, flux linkage is equal to the magnetic field strength times area times cos of the angle between the flux and the normal, times n turns. Now we may continue with changing magnetic fields. By Faraday's experiment, we saw how when a magnetic field moves near a coil, it induces a current in the wire. But a better definition would be that a changing flux linkage in a coil induces a current in the same. But how does this affect inside the wire? Well, we can observe this through an applicable example of Fleming's left-hand rule, a physical representation for simplifying logical reasoning. Fleming's left-hand rule is a way to find the direction of a force in an object when a current and magnetic field are at right angles from it. It takes this shape, and states that the thumb represents the force, the index finger is the direction of the magnetic field, and the middle finger is the conventional current. If the current taken into account is the induced current, then the right hand is used. So, if an electron is inside a conductor moving at a constant speed to the right through a magnetic field directed into the page, we could use our left-hand rule to notice that the force is downwards. From here, we evidence that there is a transfer from the kinetic energy in the movement to electrical potential, hence generating induced EMF. EMF, or electromotive force, is defined as the work done by the power supply per unit charge. It's created due to change in flux linkage in a conductor, and as the size of the EMF is proportional to the rate of change of the flux linkage, Faraday made the following rule. The induced EMF is proportional to the negative rate of change of magnetic flux linkage through a conducting loop. Or we could also say it as EMF is equal to negative number of turns of the wire times the rate of change of the magnetic flux, as you wish to say it. Now that we know what's EMF, we should get to know how to induce an EMF. The most known method is by moving a magnet or a coil into the other, as it changes the magnetic field strength made by the coil as the magnet moves, and vice versa. It could also be made by changing the area of the magnetic flux, as a conducting bar rolling along two contacts causes the loop to increase or decrease in area, hence changing the flux, as we may observe when expanding phi as magnetic field times area. And the third method is by rotating the coil. The magnetic field strength, by being a vector, it reverses the field between P and negative B, making the field strength to B. Also, this method has the advantage of being in a loop, as in the other two the magnet will pass once through the coil, or the bar will reduce the area until one point. Meanwhile, in this case, the coil may spin as much as desired. Continuing with the terms, we should get to know Lenz's law. In the examples before, we induced an EMF. The electrons in the conductor were moving. We were inducing a potential difference and a current in time. Hence, we could say that the electrical energy E being induced is equal to the current times the potential difference times time. But when we induce energy, where is it coming from? Wouldn't it violate the law of conservation of energy? It wouldn't, because kinetic energy is transformed into electrical potential energy, as when, for example, moving a magnet into a coil. The magnet enters the coil to induce a current. The current flows in the coil, causing it to generate a magnetic field and behave as a magnet opposing the moving magnet. Hence, the direction of the current always acts to try to resist the change that is happening, following in a certain manner Newton's second law. This will lead to Lenz's law, which states that the direction of an induced current is such as to oppose the charge that produces it. From here we could derive the following formula for potential difference B. As the power induced is equal to the power required, we say that current times potential difference is equal to force times speed. Replacing the force is equal to magnetic field strength times current times length into the other formula force will give us the EMF to be equal to magnetic field strength times speed times length. Lenz's law can be evidenced more when passing a magnet through a copper wire, because as the two magnetic fields oppose, a force is generated opposing the fall of the magnet, and it causes the falling time to take longer than usual. But to take a good profit of all of these concepts, we should analyze generating domestic energy. To generate electricity, we need to rotate a coil of wire within a permanent magnetic field. As the flux is given by NBA cos theta, the only variable changing the flux is the angle, resulting in a flux linkage times time graph, in the shape of a cos graph. And as the induced EMF is only generated when there is a change in the flux, only in the fragments where there is a tangent not equal to zero, EMF will be induced, resulting in a negative sinusoidal variation, as we could derive when placing the flux formula into the EMF induced formula, as shown right now. Now, if we want to change the EMF, we have four options, each one considering a variable in the EMF induced formula. 1. Increasing the magnetic field strength. 2. Increase the area of the coil. 3. Increase the number of turns in the coil. 4. Make the coil spin faster, increase the ratio. The first three would simply increase the amplitude of the sine wave, but option 4 increases the frequency of the wave as well, making one rotation to be completed in less time. As for the power made in this process, this is measured in average power. Average power is easy to calculate in direct current, as the current is constant, but in alternating current, as its name states it, the current varies by time. To get a grasp of how the power is generated by alternating current, we should use the formula power is equal to current squared times resistance. As the resistance is a constant, the current squared will result into a squared sine graph. From the graph, we could say that the peak power is equal to peak current squared times resistance, or from the other power formulas, that the peak power is equal to the peak current times peak potential difference. As for the average power, if we draw a line horizontally at half peak current squared times resistance, the total area under the line is the same as the area under the graph. So for the average power in alternating current, we could derive the following. So, average power is equal to half peak current times peak voltage, or is also equal to half peak current squared times resistance. If we consider that power is equal to current squared times R, we could also say that average power is equal to average current squared times R. Now, if average power is equal to half peak current squared times R, then we cancel the R and we place the square root at the other side. In this case, we call this average current. The root mean squared current, and it can be expressed as following. Root mean squared current is equal to peak current over square root of 2. Likewise, this can be done for the voltage root mean squared. So root mean squared voltage is equal to peak voltage over square root of 2. Likewise, the resistance will be a ratio for the potential difference to current in both formulas, as shown in the relationship. Resistance is equal to peak voltage over peak current is equal to root mean squared voltage over root mean squared current. After all of this, we get the term root mean squared. This way we say that the root mean squared of an alternating current, or EMF, is the value of direct current, or EMF, that will supply the same power in a given resistor. Transformers. Transformers are an invention made to change the voltage in AC. This works by having a first wire in the form of a coil have alternating current pass through it. As the current changes, the magnetic field also changes correspondingly. Then the magnetic field can be linked to a second coil by having a ferromagnetic core to pass through the two coils. Finally, the fluctuating magnetic field will induce EMF into the second coil, due to Faraday's law, and the EMF induced in the second wire will be the sum of the EMF induced in each turn of the coil, giving us the formula total EMF is equal EMF per turn times number of turns. As both coils have the same magnetic field, they will have the same EMF per turn, but not the total EMF. This way we may also obtain the following ratio. Primary EMF over secondary EMF is equal to primary number of turns over secondary number of turns. Now, the transformers that are set up to increase the voltage are called step-up transformers. When they are set up to decrease the voltage, they are called step-down voltage. In more technical manners, this would be a step-up transformer is one that has a higher potential difference across the secondary coil, and a step-down transformer is one that has a lower potential difference across the secondary coil. Now, by using Ohm's law and assuming the transformer is an ideal transformer with 100% efficiency, we could also derive the following ratios. And why we will use transformers in real life? They are mostly used when sending electricity over long distances. As the lower the current, the less the electrons move and the less heat generated. Also, it has less power loss. But also when wielding to increase the current to generate greater heat, and in construction sites to decrease the voltage if someone gets electrocuted not to die. As for converting alternating current to direct current, we should first make reference to the half-wave rectification. Alternating current works great to avoid high losses and electric shocks, but it's not suitable for semiconductors, microchips, as these can only operate using DC, and these semiconductors are basically almost every household appliance today. Reason why, when using electricity, AC has to be transformed into DC. The simplest way to change AC to DC is to use a diode in a circuit. A diode is an electrical component that allows the current to flow in one direction, removing the negative portion of the AC. This is called doing a half-wave rectification, as it produces half of the AC wave pattern. Now, full-wave rectification. We saw half-wave rectification, but the most efficient way to pass AC to DC is to use a full-wave rectification, as the half-wave rectification divides the efficiency by 2, way too much, basically just 50%. The full-wave rectification uses a diode bridge, a more complex series of diodes that reverses the negative parts of the AC to give a series of positive peaks, but still not a constant DC output. Reason why? we see the option of adding capacitors. To make the optimal AC to DC transformation, we should add capacitors to the circuit, as these act as a temporary battery which later discharges exponentially. So, as the capacitor charges in the peak, it then discharges exponentially and fills up the bodies in the full wave rectification, resulting in DC with a slight ripple. To decrease the size of the ripple, one can use a larger capacitor or use a load that draws a smaller current. Talking about capacitors, one should reference capacitance. What's capacitance and capacitors? First, what's a capacitor? A capacitor is a device used to store an electric charge, consisting of one or more pairs of conducting plates that are close together, usually separated by an insulator. The amount of charge a capacitor can store depends on the potential difference between the plates and the capacitance of the capacitor. Now, capacitance is the amount of charge stored by a capacitor when the potential difference between the plates is equal to 1 volt. This definition will give us the formula. Capacitance is equal to charge over potential difference. And how can we calculate energy in a capacitor? If we charge a capacitor linearly, the amount of charge stored will increase linearly too. The same way will the potential difference increase. With this relationship, we could derive the energy equation in the following way. The gradient of the graph, given that C is equal to QV, will be 1 over C. Now, if we know that potential difference is equal to energy over charge, then the potential energy difference times charge will give the energy. And as the graph is linear, the energy is equal to the area below the line, which is equal to half QV. And with the formula for capacitance, we could derive the formula E is equal to half CV squared. But which factors affecting capacitance? To consider which factors affect capacitors, we just have to evaluate once again what are capacitors. They are two metal plates with a certain area separated by a certain distance between them. Now, if we close together the distance between the capacitors, the electric fields will distort in shape, pulling the field more towards one of the plates, making the other one have more capability of receiving electrons. Likewise, if we increase the area of the plates, we will have more capacitance, more area to store electrons. This letting us know that capacitance is proportional to area and inversely proportional to distance. Hence, capacitance is equal to area over distance times the permittivity constant of the material being between the plates. This being the dielectric. Now, we've mentioned about the permittivity constant, but which material will be the most adequate to be between the capacitors then? The ideal material is what's called a dielectric. A dielectric is something with a large number of dielectric dipoles with the ability to align between each other, because when the capacitor is uncharged, the dipoles aren't aligned. But when there's an electric field between the plates, they align. Each dipole has a small electric field in the opposite direction of the electric field of the plates. But the dielectric reduces this field for the same amount of charge, increasing the capacitance.
And how are capacitors seen in circuits? Now that we have seen how capacitors are and work, we shall observe how capacitors and capacitance are present in circuits. Capacitors in parallel circuits. When two or more capacitors are connected in parallel, we have increased the area of the plates, so the capacitance increases, mathematically giving us that the total capacitance is equal to the permittivity constant times the total area over distance, or the permittivity times the sum of the areas of the first pair of capacitors over the distance between the plates gives the total capacitance, basically adding normally the capacitor's capacitance. And in charge and voltage terms, it will be like this.
As for capacitors in series, just as is stated in junction law, when various capacitors are connected in a series circuit, these share the total potential difference between them. Also, Throughout the capacitors, the charge is inverted from positive to negative, as each pair of plates inverses the charge the next one receives. Hence, with this analysis, we could say that the first capacitance is equal to the charge over the voltage it receives. The same with the second one, receiving its corresponding voltage, making the total capacitance to be charged over the total voltage. Therefore, we could represent this better by inverting the formulas and adding up the voltages, finally resulting in the general formula that is shown below. And how do capacitors charge and discharge? Now that we know how capacitors store charge, we should see how they charge and discharge themselves. Charging a capacitor. When charging a capacitor, the more electrons there are on the plate, the harder it is to add more, because the negative charges on the electron repel between each other, also repelling the incoming electrons, decreasing the current. Thus, the current while charging a capacitor decreases exponentially. When charging a capacitor, if there is no resistance, it charges instantaneously. Introducing a resistor will cause a measurable time delay, as the electrons from one plate pass to the other. Likewise, the voltage between the capacitor and the resistor is exchanged exponentially, as the capacitor begins without voltage and the resistor with all of the voltage. Therefore, by derivation, we could obtain the value of the voltage as shown. So, if the voltage of the resistor is equal to the voltage of the cell minus the voltage of the capacitor, and this is equal to IR, then I is equal to the voltage of the cell minus the voltage of the capacitor over R. The value of the charge on the capacitor as it changes in a period of time is dictated by the capacitance value of the capacitor and the rate of change of voltage because of the equation capacitance is equal to charge over voltage. So we could also say that current is equal to the rate of change of charge, and that is equal to capacitance times rate of change of voltage. Rearranging and substituting these two equations gives us that the rate of change of voltage is equal to the voltage of the cell minus voltage of the capacitor over resistance times capacitance. This makes the charging curves follow the equation voltage is equal to peak voltage minus peak voltage times E to the power of minus 1 over resistance times capacitance. Discharging a capacitor. As for its discharging process, it consists of the electrons going back from the negatively charged plate to the positively charged one, by connecting the circuits for the electrons to generate current. Thus, as the capacitor discharges the voltage across the capacitor is equal to the product of the current in the circuit and the resistance. So, voltage of the capacitance is equal to current times resistance. The current is the rate of flow of charge, so we can expand this to rate of change of charge is equal to the voltage of the capacitor over resistance. Using the capacitance equation, capacitance is equal to charge over voltage, we can substitute the voltage of the capacitor, giving us that the rate of change of charge is equal to minus charge over resistance times capacitance. The minus sign is there because after any time interval the charge decreases. So change in charge is negative. The constant here is minus 1 over resistance times capacitance. So solving the equation gives us the exponential equation of the curves we saw above. Charge is equal to peak charge times E to the power of minus 1 RC, resulting in the inverse process of charging the capacitor. Finally, the time constant. Considering RC, as we saw before in the other formulas, and how it actually gives time, we can conclude that this is the time factor, which goes with the symbol tau. And with the formulas seen before, we can finish electromagnetic induction with the three shown formulas.